He will be speaking on a topic called designing design systems for rural remote patients monitoring. This seems to be a very much needed system, okay, for people who doesn't have the resources. So let's give us a warm welcome to today's speaker, Dr. Corey Baker.
So coincidentally, I think I know almost all of you. And I think it's going to bode well because one is colleagues, and then two, many of you have either taken the class that references some of the material that we're going to discuss today, or you're taking the class currently. So I think we should be able to have some very interesting conversations today. I encourage you to ask questions during the talk, just so I don't have to go backwards. And I think it's usually easy for me to address the question as soon as you have it when the slide is up, as opposed to going backwards. So feel free to ask questions at any time. Thanks for the introduction. My name is Corey Baker, and I'm going to be talking about the work that my research lab conducts, particularly my graduate students and some undergraduate students. And I just have the privilege of taking credit for all the awesomeness that they were doing. Right? And so we'll see. Let's talk about some of these things. So designing opportunistic systems for remote patient monitoring. So here's some of the topics that we'll discuss today, and then when we get towards the end, I'll talk about how I've managed to kind of also infuse that into coursework curriculum at the undergraduate and graduate level here in the department. And so you see a word cloud here, and these are some of the things that kind of comes up when you start thinking about remote patient monitoring. So you hear about things like mHealth, and then particularly when you think about rural environments or environments with limited connectivity, you start seeing a lot of things that are issues with the network itself that's associated with it. So there's some assumptions that people typically make in the United States about how you can do remote patient monitoring that doesn't bode too well when you go to rural areas. So what's remote patient monitoring? I'll give you one more opportunity. If you have an iPhone or iOS device, if you scan that QR code, that'll take you to where you can download an app called Assuage or As You Age. And that app is actually used for IRB-approved pilot studies here at UK in partnership with doctors at the Markey Cancer Center. So we'll talk about some of those things. So you can scan that and test it out, kind of see how it is. And then when we get to the end, is that fine or too loud? It's better. It's better? Yeah. Okay. We'll also see if we have some time to go into a demo of some of this on my computer, fingers crossed, hoping that it doesn't break. All right, so what's remote patient monitoring? So the remote patient monitoring that we know, and basically how devices are enabled today, we have our cell phones that typically can communicate with a number of sensors, and then we assume that that information can get propagated to the internet, and then once it's there on the internet, doctors or nurses or clinicians themselves can actually assess and understand that information and hopefully provide feedback to a particular patient. And so what happens when you have a scenario when internet's not available? So the devices can collect the information, but either internet's not available or it's intermittent, right? And so we talk about how to disseminate information in these types of cases. So to give a background, when it comes to rural connectivity, many of us assume, particularly when we're on campus, that internet's available everywhere, right? But if you look at what's happened over the last few years, you see that 58% of rural settlers believe that there's an issue with the internet. And if you look at the amount of money that's been spent in recent years, as recent as 2020, the government has allocated over $22 billion to try to get internet to the rural areas when it gets close, basically to the what they call the last mile, right? And so even when there's internet availability there's other issues that come up related to not even just the fiber being laid to establish your internet connectivity, but can you encourage the community, one, to pay the fee, the monthly fee that's typically needed to pay for internet, like how we pay for in our homes, or if you want to reduce that cost, you have to provide an incentive to these companies like AT&T and other cellular providers to actually reduce their cost, which they typically don't want to do because it's not a good profit margin. Right? So there's a number of issues that comes up when needing internet to actually provide patient care. Another crypto I was going to mention on the slide in the middle, you see that 7 out of 10 of rural settlers actually have smartphones. Right? So we're going to be talking about what smartphones can do, but you can see that many of them have smartphones. Where they live, there's an issue with cellular data or being able to transmit cellular data. So how do you solve this problem? Well, one, this type of problem, many times as us, many of you in here are computer scientists, we attempt to understand a problem and then we may decide and start writing research papers based on it. But in reality, that paper, that piece of technology we create cannot get used. And the reason for that is we cannot solve these problems in a vacuum, right? In order to do these properly, you need to do a process which is called co-design, which incorporates all the entities involved. The technical people, CS engineers, medical doctors, patients, you have to design for the patient. I'll give you an example. If you think you designed the greatest app in the world, but nobody wants to take advantage of it, or the end user is not going to use it, one, you're not going to make money and people are not going to be able to see how great your technology is. And so there's a bunch of use cases that you can check in the past or historically about how things were designed but did not incorporate the right entities involved. You see it going all the time with machine learning now. And say sensors, I'll give you a quick example. If you look at how sensors were designed to detect when you wash hands, basically it wasn't designed for people of darker skin, right? And so if you look at, you can look this up online, if you look at the engineers involved, basically they weren't part of the data set and they weren't part of the design process. So say for instance for me, when I wash my hands, I have to use the other side of my palm typically to get that sensors to turn on, right? And so when you don't understand the right people that need to be involved when you design, it causes issues. Same thing with engineering. You can build the technology and say, hey, I'm an expert in networking, but if you don't have the medical doctors involved, if you don't have the patients involved telling you what their needs are, you cannot solve this solution properly. So the way that we attempt to address that is through, we're part of my research lab, the Network Reconnaissance Lab is part of a larger entity called Launch. And Launch is affiliated with NIH, of course, the Markey Cancer Center. The person there to your left is Dr. Timothy Mullet. He's the lead thoracic surgeon at the Markey Cancer Center, and he's also the chair of the National Cancer Commission for the country. And then also, you see Dr. Vanderpool's in the middle. She was a former professor at UK, but she's also one of the lead directors at the NIH. And then you see FCC, Amgen, UC San Diego, Med School as well. So it takes, what happens is the Launch Collective consists of medical doctors, engineers from FCC, experts, our parts in building the mobile apps and the systems. And as a collective, we do what's called co-design and ask patients questions, doctors questions on what their needs are and what they would see in the system. If you want to see more about that, you can scan that QR code and see what some of the other things that Launch works on. So symptom management, right? And so I'm going to briefly describe this because this is kind of just going to help us understand the types of data that would come into the system, and I'll show some more details on that later. So cancer patients experience, particularly I'm going to talk about cancer patients because that's what we work with, or that's what we have been working with for the studies I'm going to show you. They experience a variety of symptoms. Usually you can assess some of their symptoms by what's called PROMs, or PROM stands for patient-reported outcomes and measures. And these historically have been done, say, via survey, right? And so psychologists and others have created these paper-based surveys, and typically you might have the patient or their caregiver, their family member that's taking care of them, fill out this survey on the patient's behalf, saying what kind of symptoms they're having for that particular day, right? And then as you move forward with cellular devices, now you can imagine that you could start inputting this information into an app to, one, do calculations, but then two, get it quicker to the doctor to assess that information. So let's talk about opportunistic remote patient monitoring, where the opportunistic piece goes into when internet's available or when you come in contact that can disseminate this information, you take advantage of that quote-unquote opportunity to pass that, as opposed to pass that, say, to a next device, in hopes that that next device / person vehicle can get it to the internet in the future, right? And so in this case, you can imagine the patient's at home, they don't have internet connectivity, but somehow the information gets transmitted later to maybe where the hospital may get this information 2, 3, 5 hours later. So to describe this, I'll go briefly over what's called delay-tolerant networks, which is my traditional area of research, and then we'll talk about how we use this in the real world in systems. So quickly describing a DTN, let's say we have a patient, Alice, here. She has a number of sensors that's hooked up to her. These are typically external sensors, so they're not invasive at all, right? And they say they have Bluetooth connectivity on them, and they can basically communicate with Alice's mobile device. So say at some point in time, say now, Alice's device collects some information, and next to her is one of her caregivers, which here I have noted as row 1, right? And so in that case, they're in Bluetooth range, and I'm going to use Bluetooth ranges here because that makes it a little bit easier, and I typically, in my research lab, typically use Bluetooth. So you can think about if there's no walls, you can transmit typically within 100 meters, but if there's walls, we'll say 0 to 30. So the caregiver is around the patient, and basically via Bluetooth disseminates this information that they collected. And I'll hand wave right now, I'll say in a secure fashion. If you want to talk about security, be sure to ask me towards the end, or ask me at any point, I guess. And so at that time, the caregiver is not as mobile. They transmitted the information to the patient wasn't as mobile. They transmitted the information to the caregiver, node 1, and then some future time, let's say 5 hours later, that caregiver left, say went to the grocery store, right? And they're around other devices that might have the potential to have internet connectivity. So in this case, the caregiver passes that information, quote unquote, securely, which I haven't said what that is yet, to node 3 and node 4, which are 2 other people, and now they have the potential to deliver this information to the doctor, and then say another 5 hours later, either node 3 gets cellular connectivity, node 3, they got cellular connectivity, or node 2 somehow came in contact with the doctor or the hospital itself, right? So you can imagine that, setting the stage, these patients that are in rural areas, they typically come to Markey Cancer Center. They traditionally are located 2 to 4 hours away, and when they come to the hospital and submit their data, which I'll show in the future, they typically do that, say, once to every 45 days, right? So when you think about delay here, if this took 10 hours, which is just a random number I put up, typically they wouldn't receive it until 45 days. So a delay here is better than the 45 days. So now this is how this would typically work in a DTN. And let's talk about now the configuration that our application as Swage app sets up, and what some of my graduate students work on modeling and designing and testing in the real world. And so there's a couple of things I'm going to show here. This figure is going to look simple at first. It's going to get a little bit complicated, but I'm going to try to prop things on the screen to explain the story. So there's a few things that we're going to see. One, when you see the little yellow lightning symbol, that means that there's internet connectivity available, so how we typically use our cellular. And then when you see the red box there, that means that there's a disconnection between one device to the other. So that's typically, you see D to D here, that means device to device communication. Say we're not in Bluetooth range to send information. So you see red there, that's what that means. Blue means that at the current time that I'm going to show, I'm going to attempt to use the same example I used before. We can send information in Bluetooth range. And then the gray is the same, but it's just going to be a future time, because I'm going to talk about 2 different time steps here. All right, so those time steps are going to be T0 to T2. And let's look at how this information will disseminate. So if you see here to the left, this is going to be the first blue time window that we're going to talk about. Let's say this is anywhere between now and 2 o'clock. Right? So now 2 o'clock is this blue window to the left. within this window, we have this similar scenario that I mentioned earlier where the patient Alice, her sensor data was collected from her. It was collected on her mobile device. She passed the information to the caregiver. Currently at that time, say the caregiver was at home. They're not in contact with the hospital at all, which does have cellular communication. But within that time window, 2 windows, they leave the house and go to the grocery store, as I mentioned, and they come in contact with another node, which is just another person participating in the network, right? They have a cell phone, and they're saying that they're willing to send information when they can. Yes?
I had a question about these nodes. Do the users of those devices have to opt in or have the app as well, or is any iPhone campaign?
That's a great question. So, when using for the pilot studies, they currently would have to opt in by downloading an app. There's a couple ways that you can do that. One is having them download the medical app itself, which is not the most convenient way, right? The patient and probably their caregiver would be willing to download the app. Others just trying to do it, not as likely. There's ways that you can go around that. Is one, you can design apps that is to their liking and provide incentives. So say for instance, a social media app, so they might be willing to use an app like Instagram, and then they opt in and say, I'm willing to disseminate information if I participate in Instagram, and they don't see the data, but they're participating, right? That's another way. The other way is that if you get the cellular companies to opt in, and that's hard, right? To say they're going to run this automatically. I'll say when that's hard, but it ended up working. So when I was doing some of this stuff, when I was working on my PhD, people would say, oh, it's impossible, and I would say, hey, you could do this without routing. This is how cellular companies like iPhones and Android, or manufacturers like iPhone and Android can opt in. And they said they wouldn't do it. But if you looked at recently, Google and Apple partnered when COVID happened, and they start doing contact tracing using the same methods that I talked about back then, which is similar to what's going on here, right? And so depending on the scenario, the manufacturers and cell providers can opt in automatically, but most of them will not. You have to do design domain-specific applications to encourage users to opt in. So that's a great question. So any other questions about that? Okay. So in this scenario, we have the caregiver was at the grocery store and they disseminated to the intermediary node. But if you see the red here, there's nobody in contact with the doctor or nobody in contact with the medical entity itself. So now at some other future time, let's say 5 hours later, you have a change in the network. Basically, there was some mobility that happened, and you had the patient is not in contact with the caregiver anymore. You see the caregiver moves, let's say the caregiver went home, but you had the caregiver is moving around still, they're driving home. And you can have a scenario that one, the intermediary node ends up coming in contact with that doctor and they can forward it, or the caregiver comes in contact with the hospital, and that can happen either via cellular, right? So basically they had a cellular connection, or they came in contact via Bluetooth, right? And so that's what we call a hybrid scenario that takes advantage of nodes moving around opportunistically, passing information device to device. And then at some point, if one of them or any of them come online, they take advantage of the internet, and typically the hospitals have internet connectivity, so they can receive as soon as the internet is relevant. So that's the type of hybrid scenarios that we look at. So there's a couple of entities involved that need to participate, right? One, the patient itself, any type of networks, and I'm going to show you how we modeled some of this in real world data, and then how some of our pilot studies look. Patients, particularly when it comes to cancer patients, are typically less mobile, right? When I say these cancer patients that we work with at Markey, they're typically post-surgery. So in post-surgery, they're doing chemo, so they're not as mobile, but they are the primary data generators. You can imagine that the information that the doctors want to see come from the patient. You also have the caregiver and other local citizens, which are those intermediary nodes before. The caregivers that are typically looking out for the patients are more mobile, right? They're more willing to opt into the network and disseminate this information. And then the other local citizens may or may not be willing to want to participate in the network, but depending on the incentive or the domain-specific application, they may opt in. In addition, of course, you have the doctor and the hospital themselves. Your secondary data generators, because they may respond to the patient's data, and then of course they need to collect it to assess what's going on with the patient. And if they're the hospital themselves, they'll be stationary, they're not as mobile as the other nodes. And then of course there's other points of interest, which I didn't mention as much here, but you can imagine when I said the grocery store or Walmart in these areas, those places tend to have internet connectivity. So sometimes the goal is not to get the data or to route the data from device to device, from patient to the doctor, but to try to route it to a Walmart or a place that may have internet connectivity, because then you know the information can get to the internet, and then which will end up getting to the doctor. So let's look at first a simulation, a real-world based simulation on how to do this. So here I showed on the screen with Launch 2 of my graduate students. I'll highlight some of the things that they've done in these spaces. So the person here at the bottom is my recently defended PhD student, Esther, who's graduating this semester with her PhD. And this is some of the work that she did on modeling the behavior of how information can disseminate in these type of networks that we just discussed. So some of you may be familiar. This is Owensville, Kentucky, right? And Owensville, Kentucky, what we did was look at some of the FCC data, and I mentioned that FCC is part of Launch, the Launch initiative that we're part of. And we here we're assessing how much broadband is available, but then two, when it comes to cancer patients, how many cancer patients are in the area. So I put some information out about the population. The reason why we went into the study in this direction is that when you traditionally look at things, the delay tolerant networks, and understanding how to simulate, many people or simulate and model, many people write simulations for these type of environments, and they're unrealistic, right? And so say in my area of research in DTNs, if you look up how many routing protocols, how you send information, there's literally hundreds of thousands of protocols that's out there. And somebody will create a simulation that has an environment that's not real, and they say, hey, I compared my routing protocol to protocol X, mine performed better, so I have the best routing protocol, paper published, right? It happens a lot, right? And what happens when that occurs, and you don't understand it, there's been a lot of times, whether it's medical or military scenarios, when you actually deploy these types of protocols and systems, they don't work, right? And so people have argued that DTNs don't work in real world because of these type of things. And it's really, simulation and modeling is powerful, but if you design it, you need to design your simulation environment the right way. So going back to Owensville, you see that the population's around 12,000 people. The density per square mile is 41.76. And then you see male, female, because some of these characteristics can determine how people move or where they go. You see their age grouping, and then you also see their education level. So these things we try to understand about what actually goes on in an environment to determine how people will actually behave in Owensville to create the simulation environment. Next, there's a very powerful data set called ATUS. ATUS allows you to understand the demographics of how many people are working, when they go to work, and et cetera. So what my PhD student Esther did was create this transition matrix of understanding how people actually move around Owensville, Kentucky. And the ATUS data set has this for this type of data for many places around the country, not just rural areas. And so here, when it comes to mobility, many times in those simulations I mentioned before, they do not use accurate mobility patterns for people, vehicles, whatever in these areas. So when you don't have proper mobility, or you model mobility in an incorrect way, and then you have a routing protocol that you think works well, your routing protocol is not taking advantage of, or your routing protocol is taking advantage of incorrect model movement information, mobility information, and then your results don't mean as much, right? Or you would have to somehow prove that your results is modeling that, your mobility is modeling that real world behavior. So here, we use this transition matrix of the people moving around in an example that I showed you to model people moving in an actual environment of Owensville, Kentucky. So If you look up the paper, you look up the results, we have these things on GitHub, but here's the simulation. Here's a table that we set up this particular simulation I'm going to show the results for. Here, you see that we randomize that experiment, which is the seeds, 100 times. So here, it wasn't, sometimes you'll see that people just do one experiment or they just do a couple, right? And sometimes randomness comes into play where it looks like your results might be well, and might be doing well. And so here you see that we randomized this experiment 100 times. This was looking over a 24-hour period, seeing how much data could be transmitted in this type of network. And we compare it to cellular, because I showed you the FCC data and how cellular will perform. So we looked at the adult population, and then a couple things that I want to note here using the real world data. You see the number of patients, we varied between 2 and 10, so kind of in the middle there, right? And that's because when we looked at the data, there's about 10 patients with cancer in that area, right? And so that's important because when you think about your data generators, if you create a simulation environment and you say everybody's a data generator, right, you're not evaluating your situation. That those patients also have lower mobility, right? And so you have to limit their mobility to understand how their data will get propagated in this type of network. And then one of the other things that we varied is one, the generation rate, but then two, we also varied how many people participate in the network. So to your question that you asked earlier about are people willing to opt in, right? We looked at lower amount of the population opts in versus greater, right? So you can't force everybody to opt in if they have to download the app. You could if you're Apple or Android. But we say if you incentivize right and you increase the participation, then your network results will look like this. So let's look at some of these results. So there's two graphs here. I'm going to try to explain how to look at them quickly. One, on this first one to your left, right? Basically lower is better. This is the delay in the network, right? And so lower is better. The other graph to the right, higher is better. So if that's your delivery rate. How much of the data that was put out there was actually delivered from patient to doctor. So higher is better there, and lower is better to the left. Now, I'm going to explain one of these real quick, and then that should help us interpret the rest of the graphs. So there's three types of things that we're looking at here. One is DTN. DTN is purely propagating the information from device to device, not having any internet available, right? Then you have the hybrid scenario, which is the example that I talked about in detail. So when the internet becomes available in the middle, that information gets propagated, it gets pushed to the internet as soon as possible. So you can think about that's probably a more realistic case, right? Internet is spotty in these areas. And then the red here, UPN, is cellular. So when using the FCC data, when cellular is actually available, only depending on cellular, right? So here, I use the red line first. The red line tells us, well, do we actually need a network that I've discussed earlier, right, in this type of scenario? So if you look at red, and we look at when you have about 10% of the population participating, we see that it has a very low delay. Remember I said on this first graph, lower is better. So cellular has the lowest delay throughout this whole thing. Well, that's what we expect, right? Cellular should perform the best because if I send some data now, it should, if it's small, which it will, which we'll see in a second, we're sending small pieces, it should go immediately, right?
Question?
Yes.
Is this delivery from the patient to the doctor or from the patient to the hospital?
Great question. This is, well, we assume that the doctor is at the hospital. So in this case, they're the same. The patient and doctor is the same in this scenario. So yes, so then delivery rate, if you look at cellular, there we see that the delivery rate is extremely low. It looks a little bit less than 10%, right? And so even though it had a very low delay, it has a very low delivery rate. So you cannot depend on cellular in these scenarios, right? If you look, you can look at the graph, the highest graph for cellular is what, 20, 25%, right? You cannot depend on cellular in the rural area. This is using the real world FCC data. This is not using the network. If you depend on that, basically only 25% of the data is going to be delivered, but that 25% of the data will be delivered within, if you go up to 100, we deliver very quickly because Because remember, the internet is spotty, right? And so you can't only depend on cellular. So now let's see what happens when we look at DTNs and hybrid. Well, when we barely have anybody participating, it looks like DTN and hybrid, our hybrid example, performs that about the same. That makes sense, right? You have low participation, even if you have low mobility between a low amount of people participating, they're going to perform the same, right? You don't have a lot of people participating. But as you start increasing people participating in the network, and let's say let's go to 30%, and the reason why I point out 30 to 40% here, so 30 to 40% on the x-axis, is that if you look at 30 to 40% here, you kind of see the delay, but then for delivery rate, we start getting close to that 100% delivery rate on those, right? And so you kind of, you start getting, you start performing better, but you start getting to a point where you'll hit diminishing returns, right? And so I highlight the 30 to 40, around the 30 to 40% range. But you do get some benefits though. So with 30 to 40%, you start seeing that the hybrid has a lot lower delay, and it also has a higher delivery rate, right? And then when you start going up to 70, you see that the delay comes down, so that makes sense as well. More people are participating in a network, so the more people that participate gets your data to the destination faster, right? But at some point, even still, within a few hours, this is within hours, you'll eventually get the data to the destination. Recall that this is not, sometimes when people, when I explain this or I interpret, they say, well, what happens if the patient has a heart attack, right? And I'm going to talk more about the data we're talking about. This is not for emergency-based situations. This is for data that I said was typically delivered once every 45 days, right? Survey-based data is actually distress data, which we're going to talk about in a second, right? And we're talking about hours versus the 45 days. So it's not for emergency information. Any questions about this? Yes.
I guess with traveling from the patient to the caregiver, is there any expectation of going the other way? Versus one sort of thing?
Oh, you're talking about for the patient to the doctor or to the hospital,
Is
right?
there any expectation for the hospital to return sort of information in that period? And if so, how would you do that? Because they would have to, I guess, just guess, get back to them, or would it?
No, that's a great question. So in the scenarios that I'm explaining here, we only model when the information needs to go from the patient to the doctor. There's other work that I don't discuss on here where we kind of look at if the information needs to come back. But many times when something, so I'm going to talk about when the distress information, what happens and why that becomes, why it's important for the doctor to know that distress. But if the doctor understands something, there's an issue, and they can't respond to the app, they'll usually have their nurses or somebody pick up the phone and call that patient or the caregiver. But so we're not looking at the information getting back, because the scenario that you're talking about is now you have to create a whole nother path to go back. You're not going to be able to traverse the same path, or you're more than likely not going to be able to traverse that same path to get the data back. So that's a great question. I think there was one more hand over here. Yes.
What causes the increase in delay at 20% versus 10%?
Oh, that's another great question. So you're saying why delay increased here but then lowered and it was lower before, right? So that's a great question. And actually that question that you brought up is also another thing that people typically don't explain well in these types of networks or in DTNs in general. Read your research papers, they'll say, oh, there's a hump in the data, and the explanation for that is not clear, right? So the reason for a situation like this is you had more people participating in the network, so you increased the nodes, you went from 10 to 20%, right? But what happens is when you move that data around, you also, I'm sorry, too fast. You see that the delivery rate increased substantially, right? So you delivered a lot more data. Now you didn't deliver that data immediately. That data that wasn't delivered before had a delay. That delay is being averaged in now, that more data being delivered, right? And so you're going to have times where if you deliver more, you may have a larger delay in this type of system than if you just did it before. But that's a great question, because like I said, many times if you ask people that are experts in the area, they'll say, oh, I don't know why that happened. If you just look at the larger one, right? Or they don't explain it well. And it's because you have more data being delivered. And in the scenario, right? So that data has a delay. Once you start averaging it in that delay, it increases.
Question. How can it be that data is not delivered at all? It's still sitting in people's phones. Those people never come close enough to a place where it can be delivered? That seems unlikely.
So that's a great point. So in this case, in this scenario, when we measured in the study, if you recall on the table, we ran it for 24 hours, right? So we stopped. Now, in your case, you're saying that, well, life keeps going. There's no steady state, or there will be a steady state, right? Like basically people will keep moving. But here we said, when we stop at the 24-hour mark to stop the simulation, if the data wasn't delivered yet, it's not delivered in this case. So the way you can steady state the system is you say, you stop data generation, say after a few hours, right, in the simulation, and you say keep running till all data is delivered to meet the criteria that you mentioned. Yes.
That transmission range for Bluetooth, is that 60 on the previous slide? At the bottom, is that 60 feet, 60 meters? What is that?
Oh, so that's 60 meters. So typically Bluetooth works between 0 and 100. And so here when we did, so you see that we use a lower number that's not well, the ideal is 100, right? So ideal, no walls being there. And so we use a lower number than ideal because many times when you also run a simulation, people will use ideal numbers. Great question. Yes?
Is there a possibility that like an intermediary continues to collect data over like a significant period of time but never connects to a cellular network? Like would the data become like large enough that it would become a problem or no?
What, for that node or for?
For the intermediary, like if my phone is just continuously collecting data but never gets a chance to dump it anywhere, is there like a timeout on that data or?
So depending on your routing protocol, you may set a timeout. So that's a good question. Like, so sometimes you say after a few hours expire the data. If you had a situation where you know that's delivered, basically networking and acknowledgement, you can start expiring the data to say, hey, you come in contact with somebody that says it's been delivered, so you remove it from your buffer. It just really depends on the routing protocol. So let's look at another scenario, and then here about when the number of patients are involved, right? And so this is the same type of setup that we saw before. So delivery latency to your left, and delivery rate to the right. The only thing different here is on the x-axis a little bit different, right? So remember I said that we varied the number of patients that were in the network. And that's essential because they're the data generators. You're creating the actual data to get to doctors. So here, when you have a low amount of patients, say you only have 2 patients creating data in the network, you see the latency for that environment. Cellular, we see had the lowest delay there, but we see that it doesn't have the best delivery rate. So it's not providing the best scenario. And then as you increase more patients in there, so more data generators, you're getting more data that's going in this network. And so you see how that data gets from the patient to the doctor/hospital, right? So in these cases, that's why you see some changes when it comes to delay, because you're seeing more data being generated in the example that we mentioned before, and then you see the delivery rate of that data. All right, well, that sounds nice, right? We talked about how do you model this in the real world and understand what's going on, but then when you actually start designing these systems for people, what are the considerations and things needed involved, right? And so here, we call this area entity-centered design, which our entity of importance here is typically the patients. And to get some information on that, 5 million people over 65 have never been on the internet, right? And so sometimes people assume that, well, because they haven't been on the internet, or maybe they just received their first smart device, maybe they're not as technically efficient as people would expect. That's some assumptions that people make, right? I'm not saying they're true, but they're assumptions that people make. So they typically, in rural areas that lack internet access, low technology expertise, and so what needs to factor in is UI/user experience co-design with teams that I mentioned before. So how do you co-design and what are you co-designing for them to take advantage of? So I've been talking about data, and I've just been saying the word data, but this is what actually one of those paper surveys look like, right? So this is called NCCN, the stress thermometer. The NCCN stands for the National Comprehensive Cancer Network. The Markey Cancer Center is an NCCN-based hospital. I believe there's only around 50 of these in the country. So the NCCN designation is a very important designation. It basically means that you're a top cancer hospital in the country. And when you're an NCCN hospital, you have to do specific things. So one of the things when it comes to cancer patients is one, providing the survey and attempting to measure their distress, which is not necessarily stress. It encompasses that with some other things. So this distress survey was designed by psychologists and others, right? And they asked the patient or their caregiver, and sometimes even the nurse fills this out on their behalf. So the most important thing that Markey uses on this, every hospital kind of uses it a little bit different, is this thermometer piece to your left, right? And so if the patient self-reports a certain value on this scale, it triggers the hospital or their social worker to have to respond in a certain way. So for example, if the patient puts on here anywhere between 0 and 3, typically they don't have a response to the patient. They say, all right, their stress level is considered low. We don't have an issue. When they start getting around 5, they might start saying that we have to issue a phone call, right, to the patient. If the patient, or they should have had a phone call. If the patient hits a 7 or above at Markey Cancer Center, like I said, everybody does this differently, the patient's technically supposed to go to the hospital immediately, right? And so you can imagine that when I mentioned over those 45 days, if this survey is only being collected and you're measuring distress over time, there's times where these patients hit a high distress level very early, but the hospital does not know until the 45-day mark, right? So the patient's been distressed for a long time. Remember, I'm telling you they're post-surgery and chemo, so they're in chemotherapy. And there's many things that cause stress. Stress is what ends up causing major issues for the patients, but going through this type of surgery is life-changing, right? Many times they were working, they might have been the lead provider for their families, and they're in a situation to where now they have cancer, they have surgery, and they can't do the things that they typically do. So they end up becoming distressed in different ways, right? So that's the most important part, and then there's a number of questions that they get asked, yes or no, that they typically check. But how Markey uses that now, that's supplementary information, and the most important part is this survey, the distress thermometer part. So one of the things that you would think, since we're CS and we design systems and apps, is you take that survey and you try to translate it over to your application, right? So you create an app for it, and you say, oh, I see that paper, I can capture it now in an application, and that saves the world, right? That solves everything, right? Well, one, we know the internet part is an issue, but it ends up that these UI concerns are major issues as well. So let's talk about what that looks like once you translate some of these over to an app and what issues you can run into. So one, and I say this too, co-design is very expensive. If you mentioned the people that I said have to be involved in co-design, the doctors themselves, the patients, the engineers, the software engineers, all those people involved need to be a part of the co-design. So getting them in one place and doing co-design properly is typically a long and expensive process, right? So here what we investigate is, can you take advantage of some of the things that these manufacturers provide? In this case, we look at Apple iPhones, things like ResearchKit, which is an open source tool, and CareKit. And for this demographic, do we need to co-design, or can we provide usability that's good enough to where we may not need to go through the whole co-design process, but only understand some of it? So we did a pilot study with Markey Cancer Center patients, 30 patients. 30 patients. And we basically designed 4 different types of user interfaces using what's already available and then tweaking some. So the 4 user interfaces were designed to understand the user preferences. Basically, for this demographic, what do they see as usable? And then also learn about their technical proficiencies, and then attempt to, if that's there, close the digital divide. So if there's things that we can do in there to basically help patients understand technology at the same time while collecting information about their distress. And the most important thing when you design for usability is you want to try to collect accurate data. So I'll give you an example. If you ask your question in a very convoluted way to the patient, or you present it in the wrong way, they may get flustered and they may choose to, one, not answer, or they may answer in the wrong way because they didn't understand how you presented the data to the question to them, right? And so UI design is very important here because, one, you don't want to just collect a lot of wrong information, you want to collect a lot of accurate information. So I showed the pictures to the top right. So my PhD student that's leading this part is Ali, who's sitting over here. She does the UI, UX stuff for the lab. Her face was showing up there, but I forgot to mention. But this is the area that she works on. I mentioned my other student asked her to do the other stuff. So let's look at one of the user interfaces. So one of them is the paper one, which may not. So I think I messed up on the transition, but the paper one is the paper survey that I just showed. And you can imagine UI one is, which is the baseline. You fill out that paper survey like you typically would, but instead of waiting until you get to the doctor, we're just going to take a picture of that in your app, and then it automatically gets uploaded through the app. So that's UI1, that's what's supposed to be shown here. That's the original way, right? It's the one that the patient is most familiar with because they, in this case, they participate at Markey, it's an NCCN-based hospital. And then you can imagine it's probably the easiest to use because they're both more familiar with it. The other is a standard, right? So the standard introduces something that becomes problematic when you do things like this. That paper-based survey, the standard basically took what exactly was there and translated it into research kit-based surveys, which is supposed to be designed to capture this information. But there's some issues that occurs from doing that. So when you see that paper, one thing when the patient sees that paper, they can see everything at once, right? On that one sheet that I showed you. You can see all the questions, they can see the distress thermometer. Phones and iPads typically have smaller screens than what a paper provides. So when you see here's the distress thermometer that looks slightly different, but the patient can probably still interpret this, right? But if you see that problem list, this has now created a synchronous process that wasn't there. The patient now has to go through step 1, step 2, step 3, step 4, and doesn't all show, right? So now the ability to complete this survey takes a little bit longer through the app. One, they have to be technically proficient, and then two, you created a longer process because of this, right? Even when they want to say, my problem list is only on the last part, I have to click, 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 or tap, tap to get to that part. So we introduced an issue by just translating a paper survey over to an app that wasn't there originally. One of the UIs that Ali created and modified is a checklist version. So now it removes some of that synchronous process, and you see that at the top, basically the user or the patient can skip to where they want to go to in the survey, and it brings back some of the aspects that they had originally in the paper-based survey, right? So now they can just skip ahead. If they don't want to do something or they know exactly where to go, they just jump to it, and now they can complete it. If they only have a couple things to fill out, they complete it shorter than the previous user interface, right? So now this asynchronous provides some benefits. And then, the last one, the last one is advanced, which I'll show in the next one, is basically the most advanced UI that basically has all the touch bells and whistles of what we typically use in an app, but can cause issues because maybe the user is not familiar with where to tap, where to go, how to swipe across, right? And so that UI can be fast, but it might not be beneficial for the demographic that it's designed for. So here's one of the papers that Ali published earlier this year that was related to assessing two of those UIs, the checklist one that we just looked at and the synchronous one. So this used what's called the system usability scale. When you do UI UX research, it's one of the tools that's used, and it helps you assess the usability of your particular interface. So the way to look at this graph is that the average system usability score across thousands of apps that they use in general, give me 1 second. What they use in general is that purple line. So typically on average, when you look at applications, when they do the SUS, they typically try to reach that purple line. If you look at these boxes here, the box is UI1, which is that synchronous one, and UI2 is the orange one, which is the one with the checklist. So the middle line in front of the boxes is the median, right? So here when you see that the median, you see that at least half of the people for UI1 have a higher usability than the average SUS in other applications, right? And then the green line is the industry target. And this is what industry tries to go after when they design their user interfaces for their particular apps, right? So the green line is the industry target. So what you want to look at here is you would hope that the median would be higher than the purple or the orange, right? Because then you know that more than half of your users reported that this user interface is more usable, right? And then the other data you can say, all right, we're seeing where the other users fall that don't fall in within the median. So you see that for UI1, the synchronous one, the users say, I have problems. I don't think this UI is usable, and it doesn't meet the industry target. But for UI2, you see that the median and almost all of the data is above the average SUS score for this graph here. And then also, you see that the median of those users are actually over the industry standard for UI2. So just adding a simple navigation piece on the top, that checklist, basically allowing users to skip around, made this way more usable for the majority of the users. Yes?
Did you also measure any change in data accuracy? My guess is that the UI2 is not as accurate.
So to answer your first part, no, not in this particular study. And then I ask you a question in a second why would you assume that?
Because if you go through this navigation, you might forget about one of the areas that you might have marked on paper, but you decided you didn't notice it in the navigation version.
I think that's a great point. That's definitely possible. One of the things that I left out, so particularly for this type of survey, the most important piece is the distress thermometer part, which all users cannot skip. They have to fill that out first. So I would agree with you that it's possible that you don't put in as much information in as you would have before, or it might not be as accurate because you skipped. But how Marky's currently using that supplemental data, they're not using it to determine what to do with the patient. So in both cases, they always fill out the key stress thermometer. And yes, I think there was a question earlier on. Yes.
Yeah. What device are we assuming that they're using? Like, was there any design of choice that, like, okay, I'm going to design it for an iPhone 14, so these questions will display more because it's a bigger screen, or like designed for the iPad, which obviously you have a lot more screen size?
Yeah. So great question. So when we did this particular pilot study, the app is designed for both, because I think many of you downloaded it already, but the pilot study was using an iPad. All of them use the iPad in the particular study. Let me just mention something real quick about that, so we can close it in. So here, this graph quickly shows the same SUS score, but looking at some different pieces. So here, if a patient signaled that they never used a mobile app before, they're there in the blue. They're blue, that blue one there. And that was their usability score. So you see that patients that never used a mobile app before still signal a higher usability using the UI2. And then you also see the usability for UI1 there as well. And then orange is rarely, and then gray is sometimes, right? And so you can see we broke down some of the different types of users, in this case, to understand their usability. So going into the real world, how do you take advantage of these things? Assuage is a system that we use for research that it basically can house any type of study that we want. I didn't mention that it collects sensor data as well. I've been using sensor data as an example. It collects that as well as the patient-reported outcomes and measures that I mentioned earlier, right? Well, we also open source tools that are used by others to where you can build your own applications, right? So these tools that we put out, we do the whole full stack. So if you use that QR code, it'll take you to GitHub, and you can see our GitHub, our lab's repos, and you can build these tools on your own. So you can do the server and the app. Here's all the information that composes each of those pieces. So it's using Postgres database. It's using Docker. So basically, literally, if you go to the server one, you just say Docker up, the server's ready, the app connects to it, and you can see how your data is transmitting, assuming you have a Mac, right? So that'll work directly. And then some of you may have been here in 2020. So because of the open source tools and exposures that we've been creating with the stuff that we've been putting out, and even leveraging the open source Apple tools. If you look on Apple's repository for CareKit, which is one of the tools that we use, the #1 Apple developer is the number one contributor is the Apple developer, the number 2 person is me, the number 3 person is the Apple developer, right? And so when you look at these tools, contributing to open source provides a lot of benefit to everybody to design. And because of those contributions, Apple came here at Keeping Current in 2020, and those 2 Apple developers discussed how to build these type of systems, and then basically what some of our work does. One of the things I've left out, that you asked me a question about, is how do you do offline first in distributing this information, right? Because since the internet's not available, you can't just push everything to the cloud. So some of the things that I've done, and the reason why I'm number 2 on that list is because how do you do distributed systems when the internet is not available, right? So we basically built that in, baked that into it, it happens automatically. That was the advantage I was trying to show. So these systems, when you look at the infrastructure, kind of looks like this, right? You have a server that's sitting somewhere. You can actually test this. So the netrecon.cs, that's our real server that's sitting in the server room here. It's set up in a HIPAA compliant way. The open source tools that we put out is almost HIPAA compliant. The reason why I say it's almost is you have to house the data, the servers correctly to be fully HIPAA compliant. But we set up almost everything for you, for any, say, IT infrastructure or for anybody else that wants to build on their own. And then when you have a cell phone, it sends information. That information is load balanced between our servers here, and that's kind of how the infrastructure works and care about how to set it. I think a cooler thing with this, since we're getting close to the end, is when you start using, we put out a baseline to build sample health applications. So we say if you want to build your own and you don't want to use just Assuage, one, if you want to partner with us, of course you can use Assuage or we can help build systems up, with you, which a couple of companies have opted in, like Eli Lilly, and we have some partnerships also with Apple and some others, right? But we also use these tools, and as many will tell you here, in the classroom, right? And so then the students take the baseline of what I just showed you, and they deploy their servers on Heroku, right? So they have some cloud service, and they take the baseline app, which has some basic features in it, and then they start building this into their own applications that they design, right? They don't have, I do not put limitations on them on saying you have to build an app that looks like this. I just say it needs to be health or medical related in that space. And then you can ask around, many of the people here have been building their own apps all semester, and they all look different, right? And so if you want to take advantage of this, one, that same class is going to be offered in the spring, next spring. Some of the things that you learn in that class, we go over UI development, OOP, but then also functional programming, databases, networking, item that many of you might know, POP, which is protocol-oriented programming. All that we talk about in there using these systems. So all the students start off with a baseline, which is thousands of lines of code. They learn that system, and then they build it into their own application. And they don't work in groups, they work individually. So that's that class. And then also at the graduate level, next semester, there's another class called Designing Apps for Medical Research. This class I think is cool because, one, you're not going to only be sitting in the class with other CS majors. There's going to be people in from the med school, from other departments around the university. And in that case, you work in groups, but you learn about, one, how to create and anonymize data sets, what is HIPAA compliance, some other technology like FHIR, to basically create these real-world systems to conduct research with. So I'll end off with that because we're short on time and I want to open it up for questions. And so, how do you work this? Did I just take questions? I can fill it down.
We don't have much time left, but maybe one or two great questions as speaker always class, right? Great questions. One or two.
I have a question. Okay, Corey, I like very much this application because, as you said in one slide, it closes with the digital divide. There are many aspects of dimensions of the digital divide, and one of them is accessibility, meant as people with some classified visible or invisible impairments. Do you have any provisions for that in your current application?
No, so there's things for it, but we haven't assessed any of the accessibility stuff, the accessibility needs yet with the particular Assuage application. It's definitely important, particularly with the demographic that we're talking about, and of course if you do studies in other places, there is a lot of features that iOS devices provide that have accessibility, and which will, when we measure that, we will want to put in metrics to kind of understand how that accessibility affects how patients input data. But I think that's definitely something that we need to look at in the future. Any other questions? Yes.
Is the switch being used right now in the field?
Yeah, well, the pilot study that we had for that one just finished. That was an IRB approved pilot study. We just had another IRB approval to do another study. So Ali is planning to conduct another study in January. So right now, we're in the middle of going into our next pilot study. But it's not released in the App Store for just general use. We've only been using it when we partner with other clinicians to do a particular pilot. One last question?
So I think this was based on connectivity of urban versus rural, or that kind of access to the internet. Is there any kind of thoughts on socioeconomic access, even within rural or within urban?
Did you hear the question?
Yeah, I have a question. Well, so one, I didn't position this as rural versus urban, or the data that I showed, I didn't say it was rural versus urban. If you recall, which I think is going to take me a long time to go back to, but if you recall when I showed the slide of Bath County, I showed the socioeconomic stuff in it, right? So I showed the salary, right? So that was factored into when we modeled how people actually move and how they behave in there. I do think that's essential because, to your point, you can have a completely urban area that has similar socioeconomic constructs, and those people are without connectivity. Now, your situation gets a little bit different because you have a higher rate of mobility, right? But you have maybe just as low of a rate of internet connectivity. So my guess, and I haven't measured it, but this should be able to perform well because in situations that have lower mobility, you see the numbers. So if you have higher mobility, you should have a higher delivery rate, lower latency, assuming people opt into the network, or you incentivize them correctly to opt in. Great question.
All right. If you still have questions, you can ask questions. When we have the pieces. Right? So, thank you very, very much for your.